So we're going to continue on talking about the Coulomb force law that we introduced in the last lesson, where F is equal to KQQ over R squared, and the K is 9 times 10 to the 9 newtons per Newton meter squared per Coulomb squared, or the alternate form of 1 over 4 pi epsilon naught times QQ over R squared. And remember, when we left off last time, we said we still needed to worry about the directions of these things because they are vectors after all. So what I'm going to do is give you an example where we have some vectors involved. And a lot of this is kind of actually a review if you remember vectors well from Physics 140. And if you don't remember it well, then it's going to give you another chance to learn it. So let's consider 2-point charges. I'm just going to have two little red balls here that are each charged up somehow. And I want to talk about the first one there having a position R1 and the second one having a position R2. Those are just position vectors that would be used to describe where they are, and it kind of doesn't matter where the origin is, because the only thing that really matters to me in this case is how far apart these guys are. So the force on 1 because of 2 is really related to the vector that points from 1 to 2, or actually from 2 to 1 in this case, and we call that properly R sub 1, 2, which is R1 minus R2. To be honest with you though, all we really care about for the moment is the magnitude of that vector, and then we'll worry about the directions later on. So if that's the force between 1 and 2, it's the force that related to the charge on each of those guys and the vector that points between them, and that force is going to be attractive if they are oppositely charged and repulsive if they are like charged. Let's assume they both have a like charge here, in which case what I'm going to have is a force that is pushing that guy there off to the right side of the screen with a magnitude of F sub 1, 2, and I'll point out that there's an equal and opposite force, F sub 2, 1, pushing that guy off to the left side of the screen. This is, after all, just Newton's third law in action. Well, no pun intended, action-reaction there, because I can just switch the subscripts 1 and 2 on this, and everything else is exactly the same. Since the R1, 2 is squared, R2, 1 may be negative of it, but it gets squared, and the absolute value signs up top take care of each other. So the repulsive forces just push each other away from one another. Now let me imagine I've got another charge here. I'm going to set one down here on the x-axis. This one I'm going to put it at position 3, and instead of worrying about labeling R3, I'm just going to jump right to talking about R13, the vector that points between charge 1, that top right guy, and charge 3, the one I just introduced. So now I've got a force on 1 because of 3, and you'll notice the equation is the same except I've replaced the 2's with 3's. And R13 is the vector that points from 3 to 1. And therefore I get this little repulsive vector that points up there, F sub 1, 3. Now the key thing about electric forces is that they are additive. They're what's called superposition. They just simply add together. So the total force on that red ball up there in the top right, F sub 1 if you will, is the vector sum of F1, 2 and F1, 3. So the total force pushes off and up to the right side of the screen there. So let's treat this a little more carefully. Let's take these guys. I know how big F12 is and how big F13 is. Let's put some charges on here. Let's say each one of those guys is 3 millicoulombs, and I'm going to say that the tick marks on my axes there are each 1 meter apart. So therefore, the top two charges, 1 and 2 up there, are 5 meters away from each other. So therefore, when I plug those numbers in, I have K is equal to 9 times 10 to the 9, 3 millicoulombs, 3 millicoulombs divided by that 5 meters squared, and what I should get out of that is 3,240 newtons. If I do the same thing for F13, I'll notice I got a little right triangle there. If I want to consider the length of that vector, it's 4 over and 3 up, and a 3, 4, 5 triangle means that the vector also has a length of 5. So it's going to be the same magnitude of force. It's the same distance away. You can probably tell that kind of by looking at it. They're each 5 meters away now. So they have the same magnitude of force, but they don't point in the same direction. After all, F12 points in the positive x direction off to the right side of the screen, and F13 points kind of off at some angle that's, well, right now we don't know it. It's theta. And I've labeled it down there at the bottom because it's the same angle that triangle forms that points from charge 3 to charge 1. Well, if I look at the cosine and sine of that, the cosine of theta is going to be the adjacent divided by the hypotenuse, which means 4 steps over is the adjacent side, 3 steps up is the opposite side, and 5 is the hypotenuse. So the cosine is 4/5 and the sine is 3/5. So therefore, the components of F13 are simply 2592 newtons in the x direction and 1944 newtons in the y direction. And when I add those guys up, what I get is that F1 sums up to 5832 in the x direction and 1944 in the y direction, which if you remember how to do vector addition and finding polar coordinates from rectangular coordinates from back in Physics 140, you do the Pythagorean theorem on that, you get a magnitude of 6147, and you do an inverse tan on 1944 divided by 5832, and you get an angle of 18.4 degrees.